Hello everyone and welcome to lecture 22 of GPU computing. Today we're going to be talking about dynamic parallelism. So last time we spoke about pinned memory and we spoke about streams. We said that when we do CUDA copy, there's something called DMA or direct memory access involved. And that's essentially when some hardware can access the memory without involving the CPU. It can access the main memory directly. And when we copy between CPU and GPU, we actually use DMA. There's a hardware that copies from the main memory of the CPU to the GPU without involving the CPU. And the advantage is that this frees up the CPU to do other things. But the disadvantage is that the DMA doesn't have the capability of doing virtual address translation because that's CPU does that. So the DMA actually uses a physical address, which means that it cannot detect if the page gets swapped out. So because of that, to use DMA, we need to have a guarantee that the page that we are copying from or copying to in the main memory doesn't get swapped out. And what that means is that we have to pin it or lock it. And that's why we use pinned memory. So usually what happens on a CUDA copy is that when we copy from host to device, the CPU will copy to pinned memory, and then the DMA will copy from pinned memory to the GPU. And when we copy from device to host, the DMA will copy to pinned memory, and then the CPU will copy from the pinned memory to our actual buffer. And the disadvantage of that is that every CUDA copy actually ends up doing 2 copies. So to get faster copies, what we can do is we can allocate our memory buffers directly using CUDA malloc host, and then we have to free them using CUDA free host so that we can unpin those pages. But of course, we have to use this with caution, because if we pin all the pages now in our memory, we don't leave the operating system with pages in order for it to do the swapping. So this would degrade system performance. Another thing we talked about is the fact that the hardware that does copying from the main memory to the GPU, and the hardware that does the GPU computing, the computing on the GPU, and then the hardware that does the copy back, these are different hardwares, and they can all operate at the same time. So in the past, what happened is that when we were copying to the GPU, this is vector addition. When we were copying to the GPU, the part of the hardware that computes on the GPU and that copies back is idle. When we compute on the GPU, the parts of the hardware that copies to and from the GPU are idle. And when we're copying back, the GPU and the part that copies to the GPU are all idle. So what we can do is we can pipeline the vector addition so that we copy part of the input, and then we start computing while we copy the next part of the input. And then by the time we're done computing, we start copying back while we are computing on the next part of the input and while we are copying yet another part of the input. And by doing this, what we've done is we've essentially overlapped the computation and the copy back with the copy to the device, so that whichever one of these is dominating performance, copy to, compute, or copy back, that will kind of hide the latency of all the other operations. And indeed, we did some profiling and we saw how over here we're able to overlap the copy to the device, copy back from the device, and the kernel execution. And in this case, copying to the device is what was the dominating the performance. So we hid copying from the device and the grid execution behind just copying to the device. Okay. So these are the 2 things we looked at last time: pinned memory and using streams. Any questions about last time's material before we move on to today's material? All right, so then today we're going to look at dynamic parallelism. So what is dynamic parallelism? CUDA dynamic parallelism refers to the ability of threads that are executing on the GPU to launch new grids to run on the GPU. So if I have a grid of threads, okay, and these threads are running on the GPU, any one of these threads could itself go and launch another grid of threads. Okay, now why would I want to do that? Why would I want to have a thread that's running on the GPU be able to launch another grid?
Maybe it would be interesting from we won't have to synchronize with the CPU anymore.
Okay, so that's one possibility is if we're running on from the GPU, we can just have one thread running on the GPU and start launching all these multiple kernels. If our computation consists of multiple kernels. But what if I have many threads running on the GPU and I want each one of them to launch its own grid? Why would I ever want to do something like that?
If there's
What
some
if you
variable
gave
that we know in advance, and so we can know it at during runtime and launch a variable grid.
Right, exactly. So if I have some variable grid, a variable size grid that I want to launch, but why don't I launch that from the CPU? Right, from the CPU we launch variable grids. What's the idea here though? The idea is I have multiple levels of parallelism in my application. Okay, I have a bunch of work that can run in parallel, and each of these units of parallelism embedded inside it is also some work that can run in parallel. And that work could be variable in size. Okay? But that work could be also fixed in size. So variable in size versus fixed in size, that is important. Okay? But the more fundamental idea here is that I have multiple levels of parallelism. Okay? I have this parallel work, and then each of these units of work within it is also work that can also be parallelized. There's multiple levels of parallelism, and we call that nested parallelism. Okay, so nested parallelism is when I have parallelism, and then within each unit of parallelism I have more parallelism. Okay, and maybe within each of those units of parallelism I have more parallelism. So dynamic parallelism is useful when we program applications that have nested parallelism, where each thread discovers more work that can be parallelized as it executes. And like I said, it's particularly useful when the amount of nested work is unknown. Okay, if the amount of nested work is known, we can launch the total number of threads that we need ahead of time, and then if there's common work across a bunch of them, we can do it redundantly. But if the nested amount of work is unknown, it makes it even harder to pre-launch a fixed amount, the total amount of threads. So if the amount of nested work is unknown, we do not know how many threads we need to launch upfront. So launching a bunch of threads and having each one of them discover how much parallelism they have within them, and then themselves launching more threads is useful. Okay. Now, what kinds of applications have this pattern? What kinds of applications have nested parallelism or parallelism within parallelism? Well, there's different kinds of applications that have this, and there's two main reasons why the amount of nested parallelism may be unknown. So there's the amount of nested parallelism or nested work may be unknown for one of two reasons, or two major reasons. One of them is where the nested parallel work is irregular. In other words, it varies across threads. Okay, so different threads have a different amount of nested parallelism inside of them. And an example of this could be a graph algorithm. So in a graph algorithm, maybe I have a kind of a vertex-centric graph algorithm where I have a thread that's doing something for each vertex, and maybe these threads want to visit their neighbors, and maybe some of them want to visit the neighbors in parallel. Okay, but each thread might have a different number of neighbors, and therefore each thread visiting the neighbors in parallel is a form of nested parallelism. But since each thread has a different number of neighbors, each thread has a different amount of nested parallelism, and that's where we have this irregular nested work that is within that is available. Okay, so in graph algorithms, each vertex has a different number of neighbors. Another example is Bezier curves, for example. So Bezier curves is a computation where we draw lines based on points. So we have a bunch of points, and we draw these lines using these points. Now, to draw these lines, right, depending on the curvature of the line, we may need a different number of points to draw the line. Okay, depending on the curvature, we may need a different number of points to draw the line. And so if I, for example, launch a thread to draw each one of these lines, okay, and each of these threads is drawing these lines by drawing a different number of curves, each thread is going to need to, drawing a different number of points, each thread is going to need to have a different number of points to draw. Okay, if I can draw these, if I want to draw these points in parallel, each thread may need to launch a different number of threads to draw the different number of points that it needs to draw in order to draw these lines. So this is another example of an application where the nested parallel work is irregular. Okay. Now, another case where another kind of category of applications where the nested work may be unknown is where the nested parallel work is recursive with unknown depth. Okay, so maybe all the threads that launch all have the same amount of nested work inside of them, but what differs across threads is whether they choose to launch or not. Okay, so maybe I have some kind of recursion, and each thread may or may not recurse depending on some information that it figures out at runtime. So an example of this is tree traversal algorithms. In particular, if I have a space, for example, and in this space I have a bunch of points that are involved in some kind of simulation. Okay, and what I want to do is I want to partition my space into boxes where each box maybe has a fixed number of points. Okay, so here when I partition, I want to partition the space into boxes, and then based on how much activity is happening within one of these boxes, I may choose to partition it further into smaller and smaller boxes, or I may choose to just stop where I am. So here what I would do is I would partition the space, and then after I partition the space, I look at how much activity is happening in each box. And for this box, I figure out, oh, there's nothing interesting happening here, so I'm not going to partition further. But here I figure out, oh, there are things interesting happening here, so I partition it further. So here I don't recurse, but here I do recurse. So in this case, here I would just stop, whereas here the thread that was responsible for this box would want to launch more kind of threads to process each one of the smaller boxes inside of it. So this is a common pattern that exists. So this is we call these quadtrees and octrees when we divide spaces like this, and this is an example of where whether or not we want to recurse, whether or not we want to extract more parallelism, launch more threads, depends on the observation that we make for the particular box. Another example of this is divide and conquer algorithms, where we may take an input, divide it, and then based on the properties of each partition of the input, we decide if we want to divide it further or not. So in each of these steps, we're dividing the input into 2 equal parts, okay? But then the variability comes from the fact that we don't know whether or not we're going to divide the input further or not, okay? So there's 2 major categories. One of them is where the amount of nested work is unknown. Each thread has a different amount of nested work. The other category is where each thread may have the same amount of nested work, but what we don't know is whether or not the thread is going to launch or not. So if all the threads that do launch will have the same amount of nested work, they've launched the same amount of threads, but different ones may launch or they may not launch. Okay? Clear so far? All right, so there's actually examples of these different applications in the CUDA SDK. The CUDA SDK actually has an example for Bezier curves, an example for quadtrees, and an example for quicksort that use dynamic parallelism. So what I will do in the lecture is instead I'm going to look at graph algorithms. I'm going to see, because we've already seen BFS, breadth first search, before. So we're going to look at breadth first search and how we can use dynamic parallelism to optimize breadth first search. So I'm going to use that because we've seen it before. I'm going to use it because that example is not available to you in the SDK. So it gives kind of yet another example of dynamic parallelism. And then also I want to use it because I want to demonstrate some optimizations that we can apply with dynamic parallelism. And these optimizations are highly pronounced when we use graph algorithms. Okay. So just as a recap, in the past, we looked at multiple implementations of breadth first search. The implementation that we're going to look at today is the one that used frontiers. So in this implementation, what we did is we had a previous frontier on every iteration of the BFS. We had a previous frontier that had a bunch of vertices that were in the previous level. And what each of these vertices did is they would visit their neighbors and decide whether or not to include their neighbors in the next frontier. Okay, so here this thread has 1, 2, 3 neighbors, so it visits each of these neighbors and decides if these neighbors should go in the next frontier or not. Okay, this thread has 4 neighbors, so this thread will go through each of these 4 neighbors and decide whether they should go in the next frontier or not. So as you can see, each thread has a different number of neighbors. And what these threads were doing in the past is they were going over their neighbors sequentially, and for each neighbor, they were figuring out whether to include that neighbor or not. Okay, so what can these threads do instead? Instead of each of these threads looping over their neighbors sequentially, what can they do?
A thread can launch a warp, and each thread in the warp launched will check the degree of the neighbor and push it to the frontier.
Right, exactly. So each thread can launch you said warp, I think you mean a grid. So each thread can launch a grid of threads to visit all the neighbors in parallel. Okay, and let me let me show you the code for this. So in the past, what we had is a kernel. This kernel assigned a thread to every element in the frontier, and it loaded the vertex from the previous frontier. Okay, and then it figures out where looks at the source pointers to figure out where the neighbors of this vertex start in the source pointers, and then it figures out the number of neighbors that it has by getting getting where the edges of the next vertex start, and then subtracting where the edges of this vertex start. And then here we're looping over the neighbors, so we go from I equals 0 to I equals the number of neighbors, and then for each neighbor we find the edge. That's just going to be start I, and then we load the destination of the edge that gives us the index of the neighbor, and then what we did is we would use an atomic compare and swap to visit the neighbor, and if we successfully visit the neighbor, then we add that neighbor to the current frontier. Okay, so this is what we did in the past. And the key thing I'd like to focus on here is this loop. Okay, this loop that's looping over the neighbors, okay, it's processing the neighbors sequentially. And what we can do instead is we can parallelize this loop. Okay, instead of looping over the neighbors sequentially, we can parallelize this loop using dynamic parallelism, so that we have a thread do every iteration of this loop. In other words, we have a thread visit each one of the neighbors. Okay, is that clear? Okay, now the question is, how do we do that? This is the code that we just saw, and the key point here is that this loop that's looping over the neighbors can be parallelized. So how can we do that? Well, it turns out that the device code for calling a kernel to launch a grid is the same as the host code. So we launch a grid from the GPU in the same way that we would launch a grid from the CPU. Okay. However, when we are launching a grid from the GPU, if we have a very large number of threads, okay, we're going to have a very large number of launches. And because we have a very large number of launches, not all of these launches will be able to run at the same time. So what the device will have to do is it will have to save kind of the state for these launches in some kind of buffer until they get their turn to run. Okay, so the information about the launches will be saved in some kind of buffer until they get their chance to run. And what this needs is that it needs memory. So we need memory to buffer the grid launches that have not started executing. The limit, there's actually, because this memory that we're going to provide for the number of launches is limited, there's going to be a limit on the number of dynamic launches that we can have. Okay, and this limit on the dynamic number, the limit on the number of dynamic launches that we can have is referred to as the pending launch count. Okay, and by default, runtime by default supports 2048 launches. So by default, the runtime lets me launch 2048 grids dynamically from the GPU. If I exceed this limit, I will get an error, or I might just hang. So what we can do is, if we know that we need more than 2,000, we plan to use more than 2,048 launches, okay? Then what we can do is we can tell the runtime to allocate more memory by increasing this limit. And the way to do that is using this command that's CUDA device set limit. This actually lets me set all kinds of limits on the GPU. The particular limit I'm interested in today is the pending launch count. So if we anticipate that we're going to have more than 2,048 launches on the GPU, we can increase this limit using this command over here. Okay. Now, having 2,048 launches on the GPU is not particularly a good idea. So if we're increasing this limit, we're probably doing something we shouldn't be doing anyways. Okay, but what I will do, just to kind of for demonstration purposes, is I will increase this limit, and then later on we'll see how we can go below this limit without having to increase the pending launch count. Okay, but let me first start with the device code for launching a grid, and then I'll go back and see how we're going to deal with this limit on the number of launches that we can have. Does somebody have a question?
Yes, I wanted to ask you, when you say launch, you mean a launch per thread or launch per, is there a metric that?
So every thread on the GPU can perform its own grid launch.
Okay, so and the maximum number of launches overall is 2,048 or per thread?
That's by default, but we can increase it. That's just 48. No, it's total.
Oh, okay, okay.
Okay, so if I have 2,048 threads, each one of them does a launch. I filled it. I filled it up.
Okay.
Filled up the memory. Okay, so what I can increase it if I need to do more than that. Okay, or later on in the lecture we'll see that we should probably not do more than that. We should probably reduce the number of launches that we're doing if we're doing this many launches. Okay, but let's start by just having every thread perform its own launch of child threads in order to process its neighbors. Okay, so what we want to do is we simply, rather than have looping over this grid and over these neighbors and sequentially, we want to launch a grid to have a thread for each one of these neighbors. Okay, so here's what we're going to do. Rather than having this loop over the number of neighbors, we're going to launch a grid, okay, that has as many threads as the number of neighbors. So I need to configure this grid, first of all. Okay, I need to specify how many blocks and how many threads it has. So I'm going to start by picking a number of threads per block. I'm going to write unsigned and the number of threads per block. Let me just pick 1,024. That's the maximum that I can have. And then I also need to pick the number of blocks. So unsigned int num blocks. That's going to be the number of neighbors divided by the number of threads per block. But of course, the number of neighbors may not be evenly divisible by the number of threads per block. So I need to do a ceiling. So the way I do a ceiling is like this. I do number of neighbors, and then I can do plus number of threads per block minus 1 over the threads per block. And then I can launch another kernel. I can call another kernel to launch a grid to do these neighbors in parallel. So I can do BFS underscore, let me call it child kernel. Okay, I can do BFS child kernel, and I give it the number of blocks and the number of threads per block. Okay, and I'm going to give it the parameters that it needs to do the processing. So we'll add these later. Okay, so now what I'm going to have is I need to define my child kernel. Okay, so here I'm going to implement this child kernel. So BFS child kernel. It's going to take a bunch of parameters, so we'll enter these later. And then what this BFS child kernel is going to do is that it's simply going to take this loop and process its iterations in parallel. Okay, so what I can do is I can delete this loop from here, and I can come up here and I can paste it over here. Okay, and now, however, instead of looping, this I here is going to become the thread index. Okay, so I'm going to have unsigned int I is equal to blockindex.x times blockdim.x threadindex.x. Okay, and then here, rather than having a loop, I'm just going to have a boundary check. So I'm going to check if I is less than the number of neighbors. Okay, so here every thread, oops, I have a mistake here. So every thread takes one of the neighbors and it checks if it's within bounds, and if it is, it does the computation. Okay. Now, of course, for me to do all this, I need to have my parent, the parent thread, pass all these data that we need: the current frontier, the neighbor, the start, the CSR graph. All this needs to be passed in as a parameter, and that's exactly what we are going to do. Okay, so I'm going to copy all the parameters here. So I pretty much need everything that the parent kernel has. I'm just going to copy all of these. Paste them up here. The one thing that I don't need is the previous frontier, because the previous frontier is just read over here and it's not used later on. The neighbor doesn't need it. So I'm going to get rid of the previous frontier, but I'm going to need the CSR graph, the level, the current frontier, the current level. I also need another thing, which is the I need the start, okay, and I need the number of neighbors, okay, because those were computed inside of the kernel. They weren't part of my parameters. So I'm also going to pass in the number of neighbors, and I'm going to pass in the start. Okay. And of course, I need to the parent thread needs to pass all of these to the child grid. So what we will do is we are going to pass all of these to the child grid. So let me just copy and paste. Okay, and we're going to pass all of these, and then we're going to be ready. So is this clear to everybody? Any questions about this? So all we've done is we've taken a sequential loop and we've parallelized it. Oops. Sorry about that. My cursor went out of control for some reason. So we're going to pass in all of these parameters. Anybody have any questions about what we just implemented?
Shouldn't we increment current level?
Oh, we're doing that in the host code. So sorry, I forgot to introduce the host code. So down here, there's a BFS. There's a device. There's a function on the host. Okay, and this function on the host is looping over the levels. It calls the kernel for each level, and then it swaps it does the double buffering for the previous frontier and the current frontier, and then it makes sure on every iteration to increment the current level. Okay. So here, when we are looking at this kernel, we're just focusing on what's happening at a single level. Okay. So as you saw, parallelizing this loop was quite straightforward. All we did is replace the loop with a kernel call, and then had the loop body became the body of the child kernel. One thing though we need to do, however, is we need to make sure that we have enough. Our pending launch count is large enough to accommodate what we just did. So what we're doing here is every thread performed a launch. So we could potentially have as many threads as we have vertices in the graph. Okay, and my graph could have a lot of vertices. It could have much more than 2048 vertices. So using parallelism in this way, I probably want to increase my pending launch count to have to accommodate as many launches as I have vertices in my graph. So I'm going to come down here to my host code. So this down here is my host code, the host function, and I'm going to increase the pending launch count to match the number of vertices. So the way to do that is this function CUDA device set limit, and then we pass this limit CUDA limit dev runtime pending launch count. Okay, so we're going to call CUDA device set limit, and we're going to specify the limit that we want to set, which is CUDA limit dev runtime pending launch count. So CUDA, it's a little bit long. Okay, And then we want to provide the limit that we have. In this case, the limit is going to be the number of vertices in the graph. So we're just going to pass in CSR graph dot num vertices. Okay, and this says that make sure to allocate as much memory to accommodate as many launches as the number of vertices in the graph. Okay, is it clear? Any questions? Okay, so let's compile this and run it and see what the performance is like. Oops, I actually forgot to compile the previous version. Let me okay. I'm going to compile the old version and run it just so that you can see what the performance like without dynamic parallelism. So without dynamic parallelism on this graph that we're using, it took 14 milliseconds. Okay, now I'm going to redo all the changes. Okay, so now with dynamic parallelism, okay, I'm going to compile again, and I'm going to run, and this time it takes 130 milliseconds. Okay, so it's 10 times slower. The performance was 10 times slower. So why do you think the performance was so slow?
Because it waited until it could launch a grid to launch it, so it capped at 2048.
No, 2048 is the size of my buffer for my launches. Okay, it doesn't mean I'm running. It doesn't mean that's the max number I can run. I actually can. The amount that I can actually run is actually much less than that. So yes, I'm launching all these grids. Okay, but they're all waiting for each other to run. Okay, I can only run a small number of them at any point in time. Okay. What else could be the reasons behind this overhead? This slowdown.
Scheduling?
Sorry?
The scheduling of all these
Okay, so
grids.
it's related. So I'm launching all of these grids, so they're all going to be going into this queue, and they're going to be waiting for each other so that they get launched. The idea is I have a large number of grids that I am running, but the other thing is that each of these grids is relatively small, right? So if a lot of these vertices might have 1 neighbors, 2 neighbors, 5 neighbors, 10 neighbors. So these things all hurt my performance. Okay, and some of them might have many neighbors where the launch is worth it. So let's take a look at how we can further optimize this code to achieve better performance. Before I get into this idea of large grids and small grids, there's one thing I would like to point out. So here, this is the code that we just wrote. So one the reasons behind the slowdown is related to streams. Okay, so if you remember, on the CPU we had streams. Okay, and if we wanted different grids to run in parallel, we had to put these grids in different streams. Okay, now on the GPU now we have all these different threads on the GPU. All of these threads are launching different grids, and the question is whether we want these grids to run in parallel or not. Now, in the way that we're using dynamic parallelism, we obviously do want these grids to run in parallel. However, the part of the issue is that when we don't specify a stream, what happens is all the grids are launched into a default stream. Now, on the CPU, all the CPU threads share the same default stream. On the GPU, we actually have a default stream for every thread block. So on the GPU, for device launches, threads in the same block all share the same default stream. So when every thread launches a grid, what happens is that the threads that are in the same block actually all launch their grids into the same stream. So these threads will be kind of serialized. These grids will be serialized with respect to each other, right? Even if there is room on the GPU to launch these grids, they will not get launched because they get serialized because they're in the same stream. And the way streams work is that you need to finish what's in the stream before you can move on to what's in the next stream. Okay. So what can we do about this? Well, what we can do is rather than having using the default stream that's for the thread block, we can have a separate stream for each thread. So we can have per thread stream. Okay, so parallelism can be improved by creating a different stream for each thread and having each thread performance launch into its own stream. Now, how do we create a stream for each thread? Well, there's two approaches. We can use the same API we saw last time when we created streams. We can have each thread call create stream to create its own streams. That's the first approach. So we can use an API just like we used it on the host to create a stream for the thread. However, because this is something that might be common, we can actually change the default semantics of streams using a compiler flag. So the other approach is to use a compiler flag that specifies that we want the default stream to be per thread as opposed to per thread block. Okay? So we want to have per thread streams as opposed to per thread block stream. Okay, so let me go and do that. I'm going to switch over here, and I am going to, okay, I'm going to open my makefile. And what I will do is I am going to pass in the flag that says default stream per thread. Okay, so here's the flag. I actually need two dashes here. Apologize for that. So I have default stream per thread. And now what this will do is we'll have every thread in the block launch into a different stream instead of launching into the same stream. Okay, so let me compile this. Okay, and now I'm going to run it. Okay, and as you can see, we do get some performance improvements. Not that much, okay, because what's really hurting our performance is something else. But we still get a little bit of improvement in performance from using per thread default stream. Okay? Clear? Any questions? Okay, so then let's look at some other optimization. So other optimizations we can do. So a common pitfall is if we launch very small grids, that launch may not be worth the overhead. So here, some of these threads might have a small number of neighbors. Thread might have 2 neighbors, 4 neighbors, 5 neighbors. In this case, launching a grid and having that grid wait for its turn to execute on the GPU may not be worth the benefit we get from parallelizing over those 4 or 5 neighbors. Maybe it's better to just have the parent thread loop over those neighbors and process them sequentially. We have another problem. Not only are these grids going to create more congestion, and they're gonna cause more delays in the queues. These grids are also might be very small, right? So if I launch a grid with 4 threads or 5 threads, that means the thread block. That one thread block in the grid is going to have a small number of threads, and that thread block will underutilize the SM. Okay, so I have this problem of having many grids, but I also have these small grids. So the small grids are not going to be worth the overhead. It's more efficient to serialize them. Also, they will underutilize the SMs. And the other problem is that launching too many grids is going to cause queuing delays in my GPU. So one optimization that I can do, what can I do to avoid these pitfalls?
I can launch 1 grid per warp.
Launch 1 grid per warp. Okay, so what would that require me to do?
To have a common queue for all threads in the warp.
Okay, so somehow you want all threads in the warp to communicate with each other and figure out how many threads they all need, and then one of them launches on behalf of the others. Is that what you mean?
Yes.
Okay, yes, so that is a good optimization that we can apply. Any other optimization? If I have a bunch of threads that are on the same warp, and each of those threads has 2 or 3 or 5 neighbors.
We can check each thread how many like grids it will call, or how many neighbors it has, and if it has less than some threshold, we can just serialize it, not call the new grid.
Right, exactly. So that's another good optimization that we can apply. Okay, so two important optimizations that we can use to not have too many grids being launched and not have these grids be very small is, one, we can apply a threshold to the launch. Okay, so that if I have small grids, I don't launch them. I just serialize the work in the parent, and I only do launches for the large grids. Okay, so I only launch the large grids that are worth the overhead, and I serialize the small ones. And here, the threshold that we pick is going to depend on our data set. Okay, so what threshold we pick will depend on our data set. Okay, because different data sets, so different graphs will have, different distribution of their degrees. So what is the best threshold is going to depend on how the degrees of the vertices in this graph are distributed. Okay, so the threshold value is going to be data dependent, and this is something that we can tune. And then another optimization, which one of you also mentioned, is to aggregate the launches. So what we can do is we can have one thread collect the work of multiple threads and launch a single grid on their behalf. So maybe rather than having each thread do a launch, we can do one launch for every warp, and the threads in the warp somehow talk to each other and they put their work together and they do a launch. Or maybe the threads in the block, maybe all the threads in the block talk to each other, put their work together, and then do one launch. Or maybe the entire grid, maybe have all the threads in the entire grid or multiple thread blocks for the entire grid talk to each other, put their work together, and then do one launch. Okay. So the second optimization, aggregation, is quite involved. It's quite complicated. So we're not gonna implement it today in class. However, there are papers that you can read on how to do this, and there's kind of also a special compiler that compiles that does this kind of optimization automatically. What we will look at today is this idea of applying a threshold to the launch. So that's much simpler to implement. Okay, and let's go and actually try and implement this and see what kind of improvement that we get. Okay. So here I'm going to go back and I'm going to open my kernel file. Okay, and here I have this dynamic launch, and I'm launching it regardless of the number of neighbors that I have. Now it could be the case that I have a small number of neighbors, and in this case, what I would like to do is I would like to serialize them. I only want to launch the grid dynamically if I have a very large number of neighbors. So what I can do is the following. I can compare the number of neighbors to some threshold. I can say if the number of neighbors is greater than some threshold, okay, I'll pick 1,200 as my threshold. So if I have more than 1,200 threads, I'm going to launch the grid, okay. Where I got 1,200 from, I just happen to know that this is a good number for the graph that I am running on. Okay, but different graphs will have a different different threshold that's good for that graph. Okay, so if the number of neighbors is large enough, I'm going to visit these neighbors in parallel. Otherwise, what I want to do is I want to go back and I want to serialize these neighbors. I'm going to come back here. I'm going to get this code that I pulled up here before. I'm going to bring it back down. Okay, and I'm going to restore my loop. So I'm going to have for unsigned int I is equal to 0. I is less. Oops, I already have that. I is less than the number of neighbors. Plus I, and in this case, I do the neighbors sequentially. Okay, so if I have a large number of neighbors, more than 1,200, I will do them in parallel. Otherwise, I will do them sequentially in the parent thread. Okay. Any questions? So somebody's asking, what does the threshold depend on? It's going to depend on, different properties of my data set. So if it's if this is a graph, in this case it's a graph, maybe it depends on the degree of the distribution of the degrees in the graph. I want to pick a threshold to where I have, enough dynamic launches for the vertices with a very large number of neighbors, so that I do those in parallel, but to where I will not have, so I will filter out enough launches so that I don't overwhelm my device with a very large number of grids. Okay? And now by doing this, by the way, now we're going to have much fewer launches than the number of vertices. So in this case, the pending launch count no longer needs to be as high. All right? Let's compile this and see what performance we get by applying optimization. So if you remember, we had 14 milliseconds without dynamic parallelism, and then we had 130 milliseconds. We reduced that a little bit. So with this with dynamic parallelism, we improved that by using per thread streams. And now we applied this threshold, okay, and we're going to compile. And again, we had 14 milliseconds without dynamic parallelism, and now with dynamic parallelism, we are actually down to 6.9 milliseconds. So we get quite a bit of improvement, okay? And the reason is that these 14 milliseconds we had before, a lot of that was just waiting for that those few threads in the grid that had a very large number of neighbors. So by using dynamic parallelism, what we do is we take those threads that had a very large number of neighbors and we process their neighbors in parallel, whereas the threads that have a small number of neighbors, we just do those in the parent thread because you know, parallelizing those is not worth the overhead of doing the dynamic launch. Okay, is that clear to everyone? Any questions about this?
Professor?
Yes.
I just have a small question on the number of threads per block you chose for the grid launch.
Sure.
In this case, since the grid is not, and since we're not making use of the properties of a block, aren't we better off lowering the number of threads per block to the minimum value that can fulfill occupancy? So like here, maybe 128 or 64?
Yeah, sure. I mean, you can definitely tune this to be a smaller number. In fact, a lot of times when we do something like this, we probably do want to have a smaller number. Okay, so this is the code that we just wrote. Over here, we have a threshold where we check, and we only do a dynamic launch if our number of neighbors exceeds this threshold. Another use of dynamic parallelism is offloading the driver code. By driver code here, I don't mean the device driver. I mean basically the function that drives the whole computation. So over here, what we did is we had this this function on the host that was driving the computation by looping over the levels, and then for each level, it would call this grid, it would call this kernel to launch the grid, and it waits for it to finish, and then when it finishes, it checks if we're done, and if we're not done, it goes over, and then it calls this grid and waits for it. So here, the CPU is spending most of its time just waiting for the this grid to complete. Okay, the CPU spent most of the time just waiting for this grid to complete. Okay, and what we can do is we can actually free up the CPU by calling one thread on the GPU to do this loop. We have one thread on the GPU, will loop over the levels, and it will call a grid for each of these levels. Okay, and that way the CPU does not have to be involved in any of this. The CPU can simply launch one thread on the GPU and go and then come back when the entire computation is done. We don't have to involve the CPU in having to drive the computation. Okay. So in some applications, the host code that drives the computation launches multiple consecutive grids. And the reason it needs to launch multiple grids is to synchronize threads between launches. So here, the reason we have multiple grids for BFS is because we need to make sure all the threads finish for the previous level before we move on to the next level. Okay, so here BFS launches a new grid for each level because we need to synchronize across the different levels. So another application of dynamic parallelism is to offload this driver code. And the main advantage of that is that we free up the host to do other things. Okay, is that clear to everyone?
Professor, so in this case, offloading the driver would mean launching all the different levels on the GPU instead of doing that on the CPU?
So it would mean that this whole code over here would be executed on the GPU instead of the CPU. Okay. Okay, so let's actually implement this. So here, rather than having this BFS levels kernel, okay, sorry, rather than have this host function for BFS levels, I'm going to have it as a kernel. So I'm going to write global void, and I'm going to call it BFS levels kernel. Okay, and it's going to do the same things as before. Okay, we don't change much. Everything is the same. Obviously, the CUDA device set limit, we're not going to have it over here. Okay, so maybe I'm going to have this down in the function that is going to call this kernel. Okay, so maybe this BFS levels is just going to call BFS levels kernel. Okay, so let me delete all of this stuff. Okay, so we're not going to have the CUDA device set limit. We're not going to have CUDA memset. What can we have instead? So the reason we called CUDA memset is because we wanted to set num current frontier to 0, right? And we wanted to do it from the CPU, and this points to the GPU. So now what we can simply do is we can simply write star num current frontiers is equal to 0. Okay, so here, because now I'm executing on the GPU, okay, I don't need to use CUDA memcopy every time I want to initialize something or check something on the GPU. I can simply use CUDA set num current frontiers to 0. Okay, now I'm gonna call the num blocks. I'm gonna launch the grid. Okay, and then down here, okay, I don't need to I'm not before I was copying back from the current frontier as the number of elements of the previous frontier. Okay, so now I don't need to do this either. Okay, because now I am executing on the GPU. So rather than copying from the CPU to the from the GPU to the CPU in order for me to check this in the loop, I can simply just I can simply just load it from memory. I don't need to do a CUDA memcopy anymore. So here the num previous frontier is equal to num current frontier. So there's two advantages actually. I freed up the GPU from the CPU from having to do all this work, but also I am avoiding all these copies back and forth between the CPU and the GPU on every iteration. Okay. Now, one important thing to note here, however, is that kernel calls are asynchronous. So before, when I had a kernel call followed by a CUDA memcopy, they both went into the same stream. So the CUDA memcopy waited for the kernel call to finish before it executed. But now that I'm no longer doing CUDA memcopy, I'm actually doing just a load. I don't have a guarantee that this kernel will finish before this load happens. So what I need to do is I need to make sure that the kernel finishes. And the way I do that is by having a CUDA device synchronized over here on the GPU. Okay? And I no longer need this CUDA device synchronized at the end because, I mean, that was for the CPU to wait for the whole thing to finish, but I no longer need it. All right, so as you can see, now we have a GPU kernel where we have one thread. It is looping over the levels and is using dynamic parallelism to call a grid for every level. And then this grid that I'm calling, or calling kernel for every level, and this kernel that I'm calling is itself using dynamic parallelism to call these other kernels. So I have two levels of nesting now. Okay. Now, what I need to do is I need to call this kernel, and when I call this kernel, how many threads do I need to give it? Just one, right? So when I call this kernel, okay, I'm just going to give it one thread. So one block, one thread, and I give it everything that it was expected. Okay, so I'm going to give it a pass in everything that it needs. Okay, any questions? Everything clear? Okay, let's compile this and see how well it performs. I'm going to compile. Oops. Oh, okay. I had 2 instead of 3 over here. My terminal froze a bit. If I compile, and then I'm going to run. So before we had 6.9 milliseconds, and now by offloading to the GPU, we actually don't see a significant improvement in performance. It actually makes things a little bit worse. Okay, so here, this optimization wasn't really a performance optimization. Okay, if my GPU, if my CPU I can use to do something else in the meantime, then it might be worth doing that. Okay, but if I'm not gonna use my CPU for anything else, it's not really expected to improve performance for me to use the GPU to drive the computation. Okay, so unless I benefit from freeing up the CPU, maybe it's not worth doing it. And the reason is, if I have just one thread running, that one thread, is it going to run faster on the CPU or on the GPU?
On the CPU.
Right, if I have, because the CPU is optimized for latency. So if I just have one thread, that'll probably run faster on the CPU. Okay, so that's one reason why this is actually slower. There can be other reasons as well. But in general, this idea of offloading the driver code to the GPU is useful whenever we want to free up the host to do other things. If we don't care about freeing up the host to do other things, maybe it's not worth the added complexity to our code, and maybe it doesn't give us any performance. Okay. All right, so here this is the code also that uses dynamic parallelism to perform that uses a single thread to offload the driver code to the GPU. Another topic, just a few more short topics before we end. One of them is memory visibility. So the operations that are made by the parent thread on global memory before the launch are visible to the child. So when a parent thread writes to global memory and then it performs a launch, the threads in the child grid are guaranteed to see those changes in global memory. And then similarly, the operations that are made by the child threads in the grid to global memory. These operations will be visible to the parent after the child returns and the parent synchronizes. Okay, so if and this goes back to what we talked about. This goes back to what we did over here. So here we had a CUDA device synchronized because we wanted to wait for the BFS kernel to finish so that we can read the num current frontiers from global memory. If we don't have the synchronization, I have no guarantee that my parent kernel will see the new value of num current frontier. Okay, the changes to global memory made by the child are not guaranteed to be visible by the parent until after the parent synchronizes. Okay, so it's important to note this because sometimes when a parent writes to global memory, you might make assumptions about the child being able to see that memory and vice versa. So it's important to know what's visible and what's not visible. Another thing to note is that a thread's local memory and a block's shared memory cannot be accessed by a child thread. So if a thread block uses shared memory, okay, a thread that uses dynamic parallelism to call another grid should not pass a pointer to shared memory to its child threads. Why not?
They might not run on the same SM.
Right, exactly. So when a thread running on some SM launches a grid of thread blocks, these thread blocks may run on a different SM, so they will not be able to access that threads that threads shared memory. Okay, or the shared memory of the block that the thread belongs to. So that is why we should not use a thread's. We should not pass pointers to shared memory or local memory via dynamic parallelism. And the reason is that child threads launched by a parent may run on a different attempt. Finally, nesting depth. So the nesting depth refers to how deeply dynamically launched grids grids may launch other grids. So here a grid launches a grid, and this threads in this grid launch another grid, and then a thread in this grid launches another grid, and a thread in this grid launches another grid. So this how deeply we go is called the nesting depth. Okay, and because of some hardware limitations, we actually cannot nest these grids indefinitely. Okay, the nesting depth is limited by the hardware, and the typical value on current hardware for the nesting depth is 24. So the deepest we can nest grid launches is 24. It means if a grid launches another grid, and the other grid launches another grid, and the other grid launches another grid, we can only do that 24 times, and then the hardware will not let us do it anymore. Okay? Is that clear to everyone? Okay, so you can read more what we covered today in chapter 13 of the textbook. And that is all I have for today. Any final questions before we end? Okay, if there are no final questions, then that's all for today, and I'll see you next time. Bye, everyone.